Hello, my awesome AP Chemers. I hope your day is as awesome as you are. We are going to start chapters 8 and 9, and chapters 8 and 9 talk about chemical bonding. So, ionic bonding, covalent bonding, metallic bonding. So, as always, you'll see the learning objectives. Make sure that you're reading those, especially before the test and before your AP exam or final. There are some exclusion statements here. So these are things that you do not need to know for my test or for any exam that you take for this class. So we are going to start with the idea of bonding itself. So why do atoms bond together? Well, they combine so that they can form structures of lowest energy. Remember, nature prefers the potential energy to be low, and so atoms prefer to bond so they can form something that is lower in energy. So a lot of the compounds are lower in energy than the individual elements, and so that makes them more stable. And all this, the stability and all that, it has to do with the Coulombic attractions and repulsions between different things. So we're going to start with ionic compounds. Remember, ionic compounds are the ones that contain ions, obviously, so positives and negatives. Something loses electrons and the other one gains electrons. And so the classic example for an ionic compound is NaCl. So let's take a look at this graph here. It's been showing up on a couple of multiple choice questions on the AP exam recently. So what this is the potential energy, and it's in kilojoules per mole. Remember, the lower the potential energy, the more stable something is. That's a good thing. The higher the potential energy, it's not stable. That's not good. Then the x-axis is called the internuclear distance, and it's in picometers. So it's a distance. What does that mean? Inter means between. Nuclear obviously means nuclei. So it is the distance between two nuclei. So the distance between the nucleus of the sodium here and the chloride here. Which means really the bond length. How long is that bond? So if you look, we have three different scenarios here. Here, the two ions are really close to each other. Here, they're kind of really far away from each other. And here, they're kind of in the middle, right? So we have some attractive forces happening because one is positive, one is negative, so obviously they're going to attract each other. But we do have some repulsive forces, which are shown by the red. So the purple is the attractive forces. So obviously it's good to put them together because they attract each other. But we also have repulsive forces because you don't want their electron clouds to overlap, because an electron cloud is negative. So two electron clouds, even if you have a positive nucleus, it's not good, right? So if they're too close here, that's a problem because the electron clouds will repel each other. And if they're too far away, that's a problem because that's not very stable, because they attract each other since there's one positive, one negative. So they want to be close to each other. And so this is kind of like the happiest of all scenarios where they're, kind of in between. We know that this is the best scenario because it is the lowest in energy. So if you look at the potential energy, the lowest is going to be the best possible scenario, the most stable and the likely to happen. And so this is the most preferable because it's lowest in energy. And if I wanted to look at what is the ideal bond length, the real bond length that NaCl exists as, I would go to the lowest energy and I would go up and check what distance is this. And this is going to be my bond length, or the internuclear distance, the distance between my two nuclei that are right here. Okay, so the point of all this is to show you that this is really, there's zero. This is the ideal bond length. That is the real bond length that we have for NaCl, and we know that because it's the lowest in energy. An ionic bond is formed by metal cations that are positive and nonmetal anions, which are negative. And there are Coulombic attractions, or also known as electrostatic forces, or positive and negative attraction. Those all mean the same thing, all three of these. Those attractions are what keep the ions together. So that's the actual bond that keeps them held together. So let's take a look at an example of an ionic substance like KBr. And if I want to look at the Lewis dot structure to show what is happening and why it's happening when the potassium and the bromine bond, I can start with potassium. The Lewis dot structure is like this because potassium has one valence electron. The Lewis dot structure for bromine has 7 valence electrons, so 1, 2, 3, 4, 5, 6, 7. And you can see that it would be nice if we can take this valence electron and move it there. That way they both have a noble gas configuration, basically. And so what you end up with is K lost its electron, so it becomes positively charged. And remember, with Lewis dot structures, we draw brackets. And then we put the charge here. And then the bromine becomes bromide. It originally had 7, but now it has that 8th one. So 1, 2, 3, 4, 5, 6, 7, and 8. And you show the charge there. So this would be potassium bromide. This is just neutral potassium and neutral bromine. Let's show that same thing with electron configurations. So potassium's electron configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. Bromine is I'm just gonna for short make it into argon. 4s2, 3d10, 4p5. So you can see that both of those are not very stable configurations. This would be much more stable if we remove this, and this would be much more stable if it has one more electron. So the potassium gives that electron to the bromine to go into the 4p, and so what you end up with is K plus, which now is 1s2, 2s2, 2p6, 3s2, 3p6, and bromide, which is argon, 4s2, 3d10, 4p6. And so we've made both of those more stable, and so KBr is more stable and is much lower in energy than neutral potassium and bromine. And so that's why potassium and bromine will bond together to form potassium bromide. Let's review some of the properties of ionic compounds. So remember, ionic compounds, they conduct electricity, but only when they're dissolved or melted. Melted. There we go. Most of them dissolve in water. Not all, but most. At room temperature, they have such high intermolecular forces because of that attraction between the positive and the negative ions, and so they are really hard to get them to melt. They have high melting points, which means they're solid at room temperature, and they exist usually in the form of crystals. So they are crystalline solids at room temperature.